In this video, we're going to cover section P.3, functions and their graphs. We'll start out with just a little bit of terminology. So the first is a relation. A relation is just a set of ordered pairs in the form x comma y, where x belongs to the set of x's and y belongs to the set of y's. So probably when you learned this the first time, you had something that looked like this. Say 1, 2, 3, A, B, C, and A might be connected to certain things and B to certain things and so on. And we could say that the elements then of this mapping were 1 comma A, 1 comma C, 2 comma B, 3 comma A. Now, the next term is function, and a function is just a relation, but it's specific relations such that any ordered pairs that share an x value also share a y value. So we can see here that 1 maps to both A and C, and therefore this is not a function. If I were to get rid of the first or the second line from 1, now this is considered a function because 1 only maps to C. I could have done the same thing and had 1 map only to A. That is still a function because if the x value is the same, then the y value is the same. One way to check that graphically is using the vertical line test. So let's go back to what I had before, where I had 1 comma A and 1 comma C. That's a horrible A, but you get the idea. If I were to graph these, I made them very easy to graph. Let's call, obviously this is 1, 2, 3. Let's call this A, B, and C, just for fun. I know they're negatives, but just go with me here. If I were to graph 1 comma A, that's 1 comma A, and then 1 comma C, and 2 comma B, and 3 comma A. Now, if I were to draw a vertical line, notice I would hit 2 points. The vertical line test says if it's a function, you should only ever hit 1 point. So when I took away one of those points, now as you can see, if I draw a vertical line, I just hit 1 point anytime. The variable x in our function is considered an independent variable, and the set x is the domain, and the variable y is considered the dependent variable because, again, when we write this in function notation such as f of x equals x minus 2, what we're going to do is input the x value, the independent variable, and whatever happens here, which is the y value, is going to be dependent on what I plugged in for x. And that, of course, the subset of y that contains all the values that are mapped to is called the range or codomain. When we're evaluating a function, we need to consider an equation that's written in explicit form. So I've purposely given you an equation written in implicit form so that you could see the difference. When you have something written in explicit form, you want that to be y equals something. And y is often replaced with f of x, a function of x. So this is not written in explicit notation, so I wanted to make sure that we were able to manipulate an equation so that we were able to write it in explicit form. So for instance, I want to get y by itself because, again, y is the dependent variable. So I'm going to first subtract x from each side, and I'm going to just write it as negative x plus 10 instead of 10 minus x. And then I'm going to multiply everything by 2. And now this is written in explicit form. Now I can think of this as a function. So y is a function of x, meaning I can write this as f of x is equal to negative 2x plus 20. Now we're asked to do certain things here. The first thing we're asked to do is find f of 0. F of 0 means whenever I see an x, I'm replacing it with a 0. So f of 0 means negative 2 times 0 plus 20. Negative 2 times 0 is 0. 0 plus 20 is 20. So f of 0 is equal to 20. This translates to an ordered pair of 0, 20. F of 3, same idea. I replace x with 3. That leaves me with -6 plus 20, or 14. Again, that translates into 3, 14. And lastly, f of 2a. So -2 times 2a plus 20. -2 times 2a is -4a plus 20, and I can leave it just like that. Obviously, I could also factor out a -4, but we'll leave it just like that. Again, that one really doesn't make sense in terms of an ordered pair. I can write it as an ordered pair, 2a, -4a plus 20. But again, it doesn't make sense in the same way that these do, where we can, think visually about where those would be on the coordinate plane. Now that we've talked about implicit and explicit functions, let's talk about implicit and explicit domain. So we've talked a little bit about domain. Domain is the set of all x values that can belong to a function. And quite often, the domain is just going to be all real numbers. Any number that you feel like you want to plug it in. However, sometimes we are given an explicitly defined domain. So for my last equation, notice, or last function, I have f of x is equal to 3x minus 2, and I specify that I only want x to be greater than or equal to 2. So the domain for this function is in fact that all x is greater than or equal to 2. That is the domain. That is written explicitly because I'm telling you exactly which x values to use. However, often we need to understand how to find the domain written implicitly. And by that I mean we need to understand what kind of function are we dealing with and what kind of restrictions are associated with that function. So for our first example, I have a radical function. And a radical function, again, is a square root, cubed root, and so on. Specifically for a radical function with an even index, meaning it's a square root or a fourth root or so on, what I know about the value of the radicand being whatever's inside the radicand has to be greater than or equal to 0. Because if I take the square root of a negative number or the fourth root of a negative number, I'm going to end up with an imaginary number. Now, so this is only for even index. If it's a cubed root, I can take the cubed root of a negative number and get a negative number, and that's just fine. So how am I going to determine the domain? I'm going to take the radicand, which is x minus 3, and I'm going to say that has to be greater than or equal to 0. And I'm going to add 3 to each side to get x is greater than or equal to 3, and that is the domain. Let's look at our middle example. This middle example is called a rational function. And a rational function is just a fraction. It's a ratio. And what I know about that is that the denominator cannot equal 0. Because if the denominator is equal to 0, I'm dividing by 0, and that is undetermined or undefined, and it doesn't work. So how do I determine the domain? I take the denominator and say that can't equal 0. So x squared cannot equal 9 if I add 9 to each side. Take the square root of each side. X cannot equal plus or minus 3. So that's how I would describe the domain, is I can put in any value that I want except for positive or negative 3. Let's remind ourselves of some of the operations that can be done on functions. So what I really want to talk about is composition of functions, but it's important to understand I can also perform other operations. So we're going to use two functions, f of x and g of x, and we're going to find the sum of those functions, the difference of those functions, and then the composition of those functions. And that's where we're really looking to focus our review. If I were to add these functions together, really, that's pretty straightforward. I'm going to take 3x minus 4. I'm going to add x squared minus 3. I'm just going to combine like terms and write them in the correct order, which is from greatest degree to least. but I would get x squared plus 3x, and then I have minus 4, and a minus 3 gives me minus 7. Whereas if I were subtracting these, I would have to be very careful with my subtraction, because remember, if I'm subtracting x squared minus 3, I'm subtracting both terms, so I'm really adding a negative x squared but adding a positive 3. So this would end up giving me negative x squared plus 3x minus 1. But what I really want to talk about is the composition of functions, because this is where students tend to struggle a little bit more. And obviously this is something we're going to use a lot throughout calculus. So f of g of x means that I'm taking f of the function x squared minus 3. So recall, if I said take f of 2, you would say that's 3 times 2 minus 4. Now that's very easy. 6 minus 4 is 2. But if I give you f of x squared minus 3, that means in f, which is 3x minus 4, I'm replacing x with x squared minus 3. So I'm still writing 3x minus 4, but instead of x, I'm replacing that with x squared minus 3. Then, of course, I would simplify. So 3x squared minus 9 minus 4, which is 3x squared minus 13. The other function is also a composition of functions, so I wanted to show you both ways that this could be written. This is g of f of x, which means g of f of x is 3x minus 4. So essentially I'm taking g, which is x squared minus 3, and replacing x with 3x minus 4. So it's 3x minus 4 quantity squared minus 3. Then I'm going to do some foiling. So let's recall what foiling is. Again, if you understand how to FOIL, you don't have to show that work. 3x times 3x, first times first, is 9x squared. And then minus 12x, that's the outsides, minus 12x, that's the insides. And then last, which is plus 16, and then that makes FOIL man. Hopefully you can see the cute little face in there. And then I still have minus 3. So then doing some simplification, I would have 9x squared minus 24x plus 13. So I can see that I can do the composition in either order. Again, both of those are correctly written in composition of functions. Very quickly, we're going to look at these 6 basic functions. These are typically called parent functions. The reason I'm bringing these up is we're going to take a look at the transformation of functions. So you need to know where a function begins so that you can see what happens when I add something, say, to the inside of a function, to the outside of a function, and so on. So the identity function is y equals x. Again, this is a linear function. So we did review linear functions and square root or quadratic functions and cubic functions and so on. And that's really what this is too. These, as you can see, this first row, we actually reviewed these back in section P.1. So the identity function, which is just a linear function, the squaring function, which means y equals x squared, and the cubing function, y equals x cubed. The reason that these are going to be important is because, again, we're going to look at transformations. So we want to know what's the difference between if I take, say, x plus 2 squared as opposed to x squared plus 2. Because I'm adding 2 in each one, but they're going to do different things. Or what happens if I take negative x squared, or y equals negative x squared. Are those the same or different? So you get the idea that it's important to know the parent function. So the first 3 we already kind of reviewed, again, back in section P.1. Let's look at the square root function. Again, that's y equals the square root of x. Again, an implied domain would be that x has to be greater than or equal to 0. Absolute value function, y equals the absolute value of x. This one is just like y equals x, except for this left-hand side has been reflected over the x-axis. And then the reciprocal function, which is y equals 1 over x. And we can see that that's also called an inverse function. Let's go ahead and review some transformations of functions now. And we're going to look at first just the parent function. So the parent function is, I have chosen the squaring function that we just reviewed. So y equals x squared. And now I want to take a look at how to transform that or how to move that. So transformation is either shifting it right or left or up or down or reflecting it across some axis. So taking a look at just moving it right or left, I want you to think about the horizontal shift the same way we thought about composition of functions. Notice it says f of x plus or minus c. So what I'm doing is I'm replacing x with x plus or minus some value. And that's why this first, or I guess second function that I have here, y equals x minus 2 quantity squared, notice that the x minus 2, that whole expression is being squared. And that is why it's shifting right or left, because I've replaced x with x minus 2. So the whole expression of x minus 2 is being squared. Same thing with if I changed it to plus 2, notice plus 2 shifts it to the left 2 units. That's different than a vertical shift. So notice the difference between where I've put the plus 2 with the horizontal and vertical shift. Again, for a vertical shift, it says take y equals f of x, which means take the whole function that you had before and then add or subtract however many units. So notice what happens here. If I add 2, it's just taking the function and moving it up 2 places. So again, I didn't change the function itself. Y equals x squared was the original function. Then I'm just adding or subtracting. Same thing, I could do minus 2 and it would move down. So let's go ahead and change it back to plus and take a look at now reflecting. So if I'm reflecting, and I think I've lost one of my initial setups here. If I'm reflecting over the x-axis, if I reflect over the x-axis, it says take negative f of x. So f of x is x squared. It's saying put a negative on the outside of it. So notice this is still just x squared, and you don't have to think about, you could put this in parentheses, really. So it's negative of the function. That should reflect it over the x-axis, and that's exactly what happened. So essentially it's taking any of the positive y values and making them negative. It's just changing the sign of the y value. Notice how different that is from reflection about the y-axis. About the y-axis, it says take f of negative x. Again, that means in your function, replace x with negative x. So notice the difference between how I've written these two functions. I've replaced x with negative x. Now, without graphing it first, let's think about what's going to happen if I reflect this function over the y-axis. The stuff on the right is going to reflect over to the left, and the stuff on the left is going to reflect to the right. And so essentially, it's the same exact function. And that's exactly what we got. The last one is a reflection about the origin, and that one must have gotten deleted on my last attempt when I messed up. This would be a negative function and replacing x with negative x and squared. And as we can see, that's actually the same as the reflection over the x-axis. And again, the reason that it worked out that way is because the reflection over the y looked the same as the original function. So real quick, let's just practice one more. Let's say my original function is x. Let's go ahead and use x plus 2 quantity squared as the original function. And let's talk about how we can do the reflections, because those can get a little bit tricky. So if I want to reflect this function, this new purple function, which has already been shifted to the left 2 units, I want to reflect it over the x-axis. It says take negative f of x. So this is f of x. I just want to make it negative, so I'm going to just copy this, and I'm going to make that negative of all of that. And what do I get? I get a reflection over the x-axis. Now, how would that be if I wanted to reflect it over the y? It says replace x with negative x. So let me just do this, and I'm going to replace x with negative x. And now that should shift it over the y, and it has. Now, how would I reflect it about the origin? Again, let's start with my original function, and it says let's put a negative in front of the whole function, and let's also make x negative x. Now, where do you think this one's going to go? Well, remember, it's really a rotation of 180 degrees, so notice it just rotated around the origin 180 degrees. Hopefully that's a good review for you of the transformation of functions. Up next, we're going to finish our review chapter by taking a look at trigonometric functions.